All right, and we should be starting any second now.
Okay.
Wait for the stream has begun. And looks like it's coming up on EventMobi now.
Excellent.
Oh yes, good memory to get that up, Kaley.
Okay. So welcome to everyone to part 2 of our 4 parts in session 601, Satellite Earth Observation, a unique view of our planet at a critical need for Canada. I'm Kaley Walker from the University of Toronto, and my co-chair is Alec Casey from Environment and Climate Change Canada. You'll notice we're in different places, as most of us are on this session. I happen to be in the Netherlands for an ESA MAG meeting at the moment. But while that is true, I want to acknowledge the land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and I'm grateful and privileged to have the opportunity to work on this land. So for our next session, we're going to be moving from atmospheric, strictly on atmospheric composition towards looking at more broadly radiation, clouds, and aerosols. So our first talk, I will hand over to Alec to introduce. And Kyle, can you get your slides up, please?
Thanks, Kaley. Hi, everyone. I'm Alec Casey, Meteorological Service of Canada, and happy to introduce a colleague of mine, Kyle Ziolkowski, who will present on the use of satellite imagery for operational forecasters, observations, and future needs. Take it away, Kyle.
There, I'll unmute myself first. Hi, everybody. You can see my screen okay? Just to double check.
Yep.
Okay, perfect. I'll get going then. Yes, my name is Kyle Ziolkowski. I am a operational forecaster / research meteorologist with Environment and Climate Change Canada. I work out of the Storm Prediction Center in Winnipeg. And my talk is going to be about mainly going to focus on just how we use meteorological satellite data in an operational forecast setting, and kind of focus on those strengths and limitations that we currently work with satellite data, and kind of what the future holds, and how do we press forward and kind of jump over some of the hurdles that we face. And when we use satellite data, it's kind of, we look at anywhere from like large scale circulation patterns, as I kind of show here, where we highlight some things like atmospheric rivers, where we can kind of combine that with geostationary data with polar orbiting data, to kind of observe things like that will be impactful weather, particularly for coastal cities, and down to finer scale features such as thunderstorms and hurricanes. So I'll kind of show examples of that from different points of view, and kind of things that we kind of try to focus on. So currently the geostationary satellites that we use is the GOES ABI series of satellites. So we have GOES East and GOES West, which is labeled 16 and 18 respectively. And really, since ABI came on board, the spectral resolution really has changed the game for us as forecasters, where essentially it's doubled. And that's just really increased the amount of information that's available to forecasters and science. And I want to highlight that the science part is also important, because as scientists, we could take that data, make different types of products, or combine it with different types of data to kind of, then feed back into operations just to help, improve forecasts. Satellite, we use it a lot for short-term forecasting and observations to kind of help verify against models, or try to observe, in areas that, are lacking in other types of observation. And I kind of show that here, where we have a lack of radars in northern Manitoba. There's just no radar data available. But we can use something like day club phase distinction RGB, which kind of shows gradation between low clouds, which are cyan, that kind of grow vertically and change color as they grow. And where they start to turn green, the cloud tops will glaciate. So we can kind of infer from that these clouds are likely precipitating. And up in the top quarter here is our internal software iris that we can use to observe where stations are reporting precipitation, and they'll show up as green dots when they do. So you can kind of highlight how the satellite can really help us track, areas of precipitation that are void of radar. And even Flin-Flon is this little lightning bolt here showing up. It's reporting a little convective storm. And just the magenta circle down here just kind of verifies what you're seeing a little bit more, where you have some more active organized showery activity in southeastern Manitoba, and you can check that against satellite. ABI has also increased our ability to view in the Arctic, which is just kind of shown here. Like you get really nice satellite imagery, over the eastern Arctic. It doesn't cover all the way up into the high Arctic. It kind of, northern Baffin Island is kind of just, just around the Arctic circles where it really starts to kind of fade away, and you don't have as good of data. So still viewing angles limit our detailed observations at these higher latitudes. And I'll show kind of more examples of that. Pose is still very much a part of what we look at, although it's becoming less and less, it seems. And there's reasons for that, but things we'll look at are like gridded new caps data. Tools like this are useful, but we don't have any internal software able to view them, to view this type of data. So it's challenging to get into the hands of forecasters or get forecasters to use it. So that's a hurdle that we have to kind of overcome in the future here. And also the temporal resolution of pose is just kind of, it just makes it really difficult to track clouds when you just have very few pose observations in a day. GOES gives you that continuous look, but parallax in those viewing angles can really change your interpretation and decrease the detail of the cloud properly. So here's an example of a large low pressure system, sitting over top of southern Baffin Island from a pose image, where you have, smoke wrapping in around the dry slot of the low, and this strong convection that's occurring over Pengerton. And at this time, Pengerton was down at like 1/8, heavy snow, where you're having this kind of convection occurring right over top of the community. And that's detail you just can't get from GOES observations. And I also show kind of this lake effect streamers coming off Great Slave Lake from GOES West. And you kind of see that there is some, precipitation occurring as you kind of get that same gradation of the cyan to green. So there is some precipitation occurring there, but with the pose image, you get much more detail and kind of understand where, what the structure of those streamers looks like. And as I said, with GOES-R and with ABI, the multispectral products have just really kind of blown up with this new technology. So there's several different RGBs out there that can, look at different types of phenomena, and you can take it and you can combine those products with different products to kind of highlight features. Like, take for example the fires here in the bottom right corner of my screen, where we take level 2 fire radiative power and you can overlay it on a true color map to kind of give you a sense of where the most intense fires are occurring that are, burning in forested areas that are producing tons of smoke. And this, feeds right into our air quality models and also into our local air quality forecasts, which we are responsible for as forecasters. Blowing snow is another really good example. I show kind of a quick loop here of where we have blowing snow is now like clearly visible. And we can create things like a blowing snow RGB to kind of highlight those blowing snow plumes and that are reducing visibility across a broad swath, a broad area. And also we can create more compelling products like the geocolor product here that kind of is more for general use, or that we can present to a general public person that might the interpretation is a little bit easier, just given just the simplicity of the imagery. The other thing that we look at a lot are mesoscale domains, and these things are really, important, and they're powerful tools for vastly evolving weather. So for those of you that maybe are unfamiliar with mesoscale domains, they're a small area domain that the GOES satellite will scan over, and there's only 2 domains per satellite, so 2 for GOES East and 2 for GOES West. But they also take National Weather Service takes priority of where they are placed every day. So these are windows that move around the full disk. And we do have the ability to request these scans at Environment Canada to use it so that forecasters can use them. Right now, we currently have to go to external sites to view them, but we've made steps to deliver that imagery to our forecasters, and that'll be coming soon. I'll expand on that here shortly. But when we're thinking about these things, like or using this imagery, this imagery is great for things like if you're looking at a hurricane, like what's that inner eye wall structure? That kind of gives you an idea of the intensity, or how the storm is behaving, or what the outer bands of the storm looks like. Or we can use it in like this imagery here in the bottom right, again, where we can track a supercell moving across southern Saskatchewan. We can see its evolution a lot clearer, like how that above anvil cirrus plume looks, which are indications of severe weather, and as well as things like the development of inflow feeder clouds, which will are signs of intensification. And there's also new tools being developed with on the mesoscale domains, such as dense optical flow winds, which take successive images and next to each other, and you can derive motion from it around. So it really gives you an idea of the flow field around convective storms. Like take for example this image here in the bottom. It's colored by where you have the cool colors represent slower speeds and the warmer colors represent faster speeds. So you can kind of see here the storm has strong divergence at the top of the storm, which is indicative of a really strong updraft, which could we'd be producing, in this case, it was producing, 3-inch hail and also a tornado. So really important tools for us as forecasters, and trying to get these in the hands of forecasters is also a challenge. And also just having priority to this type of imagery would be great if we had something similar to that, or just if they could expand the domains, but it doesn't appear to be the case right now with the current GOES satellites. So what are our current development activities that we're doing within Environment Canada to kind of help with some of these limitations, and just mainly getting imagery and getting products to forecasters? One of the main things I'm working on is development of WMS satellite imagery. So we've created products for various clients for prediction services, aviation, vegetation, fire, smoke, pollution, as well as the Volcanic Ash Advisory Center in Montreal. So the WMS affords us the kind of luxury to do lots of product testing and development, and then provide it, to our processing software. And from there, we can feed it into GeoMet, which is an internal and external facing WMS server. And from there, it can feed several different clients, anywhere from like forecasters to just, weather office or external, public users. And so it provides that kind of flexibility. And we're also undergoing a post network renewal. And so we wonder if, taking some of this idea that we're creating all this WMS imagery from geostationary satellites, can we apply this to post to help kind of bring that back into operations a bit more, maybe than it currently is now, and kind of provide that, education as well to maybe newer forecasters that are not as familiar with it. One of the big things that also I work on is mesoscale domain, the mesoscale scan development. Providing that through WMS is a big part of what I'm working on. We have I kind of show kind of an example here through our internal viewing software, which is Nino. So you can layer it in through there. We can layer over and put over top other observations along with it. It's kind of our our primary software that we use. I'm also starting to play with the dense optical flow development to kind of maybe see how that works in Canada, and how is that something that forecasters would be interested in leveraging. All this data is also available through GeoMet and MSC Open Data. We're introducing a bunch of new products here in the coming weeks. Currently, we're kind of have a limited set. I left some links on here so people can go check it out. It's all publicly available. And also coming along with those is we have some product information guides that we've developed on just kind of give general descriptions on how a user would use the data. A lot of these information guides are already available from the United States, and NWS provides a lot of this stuff. But we kind of went with a more general route on just like how you can use it and what to look for. Because when you look at these things, they might be complex to just a general user, but how do you but they're also packed full of information that they may find useful. Just to kind of wrap up quickly, so kind of the future needs of us as forecasters is we really need better data in the north. Resolution and parallax effects really inhibit a lot of what we do, particularly in the north. Take for example here, this is a snow fog RGB imagery, which we use to kind of detect blowing snow. And because of limb effects, as you're kind of moving towards the edge of the disk, you get a lot of limb effects. And so that changes the interpretation. So, a newer forecaster or an inexperienced forecaster may not, see that may not understand that and might miss like the actual extent of a blowing snow. So I seen Ray Nasser is doing a talk on AOM in the next session block, I do believe, and it's I'm gonna maybe promote that here because that is a really, I think AOM is a really key mission for us as forecasters to have to going forward. And tools to view the data. A lot of forecasters, they use different ways of viewing the data, like static imagery from just websites. You know, that is great for performance and looping and for low bandwidth users. But WMS provides that flexibility, and you can layer data over top, but it's at the cost of performance because of the way that the data is structured, and it can be slow to loop, let's say. And also kind of the question I battle with is how do you better integrate satellite data into briefings? Like if you're briefing a client on RGBs, they're full of this fantastic information. And so how do you, convey that? Because it's complex to look at and it's false color in nature. So trying to figure out ways to kind of get them on boards to kind of provide that information so that, an external user might be able to, be more comfortable with the use of that. So I see that as kind of a hurdle, but maybe these fact guides or these product guides will kind of help with that a little bit. And one last point is satellite data is really heavy, and we have to think about the future, going into the future. And what I mean by heavy is that the file sizes are large, and how do you that increases processing time, and how do you build tools to handle that type of volume of data? Because with future imagers, with increasing resolution and larger file size, it's just going to be harder to move that data around. But this is all I have. It's a very high level talk about how we use data. It's hard to squeeze all this into 15 minutes, but if there's any time, I'll be happy to take any questions.
Thanks a lot, Kyle. We do have one question in Event Mobi, so I know we're a minute over, but we took up some of your time with the introduction, so we'll give you the one question, and then we'll move on to the next talk. So the question was, would hyperspectral rather than multispectral long-wave IR sounding with rapid revisit, example from GEO or HEO, bring any useful new information if it were available for ECCC forecasters?
I think absolutely. We see that with some of the products like that are available from POEs with hyperspectral soundings that are on board there. I think having that type of data at our fingertips would be absolutely critical. Because I can only imagine the type of products that could be developed, as you see with ABI already, like just with the increased just spectral resolution and the things we can do with it now. It's a fire hose of information, but it's also very, very useful information. I would say absolutely yes.
And we'll hope for good success for the GeoXO program in the US, and they're a new central satellite that would have a hyperspectral imager or hyperspectral IR sounder. And I know
yes.
our numerical weather prediction folks as well are extremely excited in this growing capability in the satellite Earth observation sphere.
Yeah.
Thanks, Kyle. We'll keep moving now. We'll head over to Zhipeng for a talk on pre-launch broadband radiative closure assessment for the EarthCARE mission. So take it away, Zhipeng.
Hello, good afternoon, everyone. Can you hear me?
Yes, we can hear you, and we can see your slides. They're in
Okay,
PowerPoint mode, not full screen yet.
Yes.
There we go. Thanks.
Okay, good afternoon again. My name is Zhipeng Qu from Environment Climate Change Canada. And today I will talk about pre-launch broadband radiative closure assessment for the EarthCARE mission. Before start, I want to thank my co-authors from ECCC, ECMWF, and then University of Leicester. So before going further, I just want first to announce a good news that after almost 2 decades of preparation, EarthCARE satellite was finally launched last Tuesday, May 28th, from Vandenberg, California, using SpaceX Falcon 9 rocket. And then during the same day, also the first communication signal was received. And then on May 30th, JAXA also confirmed the full deployment of the CPR antenna reflector, which is also great news. And then for the next 2 weeks, ESA and JAXA will continue working on switching on different payload of the satellite. So for the scientific objective of the EarthCARE mission, we want to study the relationship among cloud, aerosol, and radiation. And there are 4 main instruments on board the satellite. They are atmospheric Lidar, ATLIT, cloud profiling radar CPR, multispectral imager MSI, and then broadband radiometer BBR. And the first two instruments are active sensor. They can retrieve the profile of cloud and aerosols, and MSI instrument will also contribute to the synergetic retrieval of cloud and aerosols. It also provide cross-track information of the satellite's nadir track, and so that they can help to construct the 3D cloud and aerosol scenes. And the BBR will observe the upwelling shortwave and longwave fluxes, which will be used for the radiative closure assessment. So ECCC's contribution to EarthCARE satellite have been quite long, more than a decade ago started. And then we are focusing on the radiative closure assessment development for the satellite algorithm and then processors using both 1D and 3D radiative transfer model. And then this closure assessment will provide crucial assessment for the performances of the satellite mission and also give feedback for upstream scientific team. And this is also the first operational use of 3D radiative transfer model for remote sensing, which will certainly enhance our knowledge of radiative transfer and its interaction with cloud and aerosols. So here I want to show the different processors of the radiative closure assessment. The first one is called ACM-COM, which is create level 2 composite atmosphere, prepare surface property, and it will also read in the synergetic retrieval of cloud and aerosols. And ACM-B3D will construct 3D scenes for the radiative transfer calculation, and also screen the assessment domain. The output of ACM-COM and ACM-3D will be used in ACM-RT to conduct 1D and 3D radiative transfer calculation. And the simulated fluxes will be then compared with the value observed by BBR instrument, and then the analysis will be conducted in ACM-BDF processor. And for the most part of the level 2 algorithm development, most developers are using those test scenes, so-called test scenes. They are generated by high-resolution NWP models, and the advantage of using this data is that they could have very high resolution at 250 meters, and then they can provide the truth to check the algorithm results. And then we use radiative transfer calculation act upon those simulation test scenes to generate and subsequently generate cloud aerosol retrievals and the radiation retrievals. However, the disadvantage of this way of doing test is that we only have 3 test scenes, and to generate them is also very costly. So the number of cases is very low. So in this study, in order to have more real case study and then to facilitate more robust statistic analysis, so we use the H1 satellite data to do those tests. So we use CloudSat, Calypso, and MODIS together with Aero 5 data, and then use them in an algorithm called Captivate, developed at ECMWF by Mason and L. And then this algorithm will produce a product called CCM-CAP, and it is the synergetic retrieval of cloud and aerosols. So these data will be used in ACM-COM. Also, in order to construct the 3D cloud and aerosol scenes, we use MODIS radiances to assist that. And then for the reference, series observation data will be used as the reference to check with the simulated data. Here are the results. The first row is for the ocean case, the second row for land case, and then the first column is the sample size for 4 different categories, from cloud fraction equal to 0, blue line, clear sky, to overcast case, purple dashed line, AC equal to 1. So the second row is the mean bias differences between the 3D flux, 3D Monte Carlo simulated fluxes and 1D fluxes using 3D minus 1D. So probably the first thing you notice is this very large negative bias in purple dashed line. both for ocean and land cases. This means that 3D fluxes is always smaller than 1D fluxes. This is probably linked to the effect and phenomenon of photon entrapment, as shown by Hogan et al. 2019. That means in the 3D radiative transfer simulation, the complex texture of cloud, especially the side of the cloud, will entrap more photons. So there will be less reflected by the clouds. However, in 1D single column approximation, this phenomenon will not be represented. And another interesting part is for this partially covered case with cloud fraction above 0.5, this yellow line. So for the ocean case, the bias is quite small. However, over land, the bias is almost as large as overcast case. This also suggests in the land and ocean, the cloud regime would be quite different. Probably over land is more convective, and then the cloud are more structured. Oh, sorry. Sorry. And then for the partially covered case with cloud fraction below 0.5, as shown the red dashed dot line, we have positive bias. So 3D is higher than 1D. This is probably linked to the leakage of radiative flux. For example, around the assessment domain, there are presence of clouds outside of the domain, but these clouds will reflect radiation into the assessment domain. Therefore enhance the 3D fluxes. And using 1D simulation, these phenomena will not be represented. So that's why we have positive bias here. And the last column is the difference between 3D radiative transfer simulated flux and series observation. So if all case included, for shortwave, we have a bias of about 4 watts per square meters, standard deviation 58 watts per square meters. For long wave, not showing here, but the mean bias is -8 watts per square meters and standard deviation of 15 watts per square meters. And the two figure below just show the similar results, mean bias for ocean and land cases. First, for blue line with clear sky, we have a slight underestimation as negative bias. Both for ocean and then land. And there are some large bias here, but it's linked to the diagnosis of snow and ice. And then their total number is quite small. But this negative bias, we still don't understand fully. So there's something we need to continue investigate during the commission phase of the EarthCARE. However, the largest bias is from overcast case, as you see this purple line, both for ocean and land. I should note that this value is 3D value. So if I use 1D value as shown here, the bias will be even larger. However, what is the cause of this positive bias? Here, I show the results for overcast case over ocean only. And then the top two panel shows the results for different cloud top pressure. Blue line is with cloud top pressure above 200 hectopascal, so mostly high ice cloud. So for this case, you will see that we have quite consistent negative bias. However, the largest bias is coming from those mid-level clouds between 400 and 800 hectopascal, as shown purple dash line and then yellow line. For low clouds, we also see a lot of positive bias at different latitudes. The lower two panels just show the similar results, but for different cloud phase. So blue line is ice phase. So ice cloud always have a negative bias, but liquid and mixed phase cloud, we have very large positive bias. So in order to help to understand what the meaning of these statistical results, here I have an example for February 20th, 2007, and over the Indian Ocean. The first two panel is the shortwave and longwave fluxes. A black line is series data. Red circle is 3D fluxes. Blue cross is the 1D fluxes. The third and fourth is retrieved ice water content and then liquid water content. And the last two are the shortwave and longwave radiances. For the large part of section in the northern northern side, there's quite good agreement between observation and simulated fluxes, as you can see in the first two panels. However, if you look at the region around 35 degrees south, you probably notice this significant overestimation of simulated fluxes, both 1D and 3D. This corresponds to the presence of liquid ice water content and liquid water content above mountain layer. So it seems the simulated flux is very, very sensitive to how the retrieved cloud was partitioned into liquid and ice. So even slight presence of liquid cloud will enhance quite a lot the simulated flux. So this is something need to be checked during the commissioning phase through, for example, cover campaigns. And we also see other locations, for example, these highlighted two red box region. These are lower liquid clouds, and they correspond to overestimation as well, as previously studies showed. Another example, also we can firstly find similar regions of those liquid clouds, which correspond to the overestimation of shortwave flux. But these two blue boxes just highlight the area where we see mostly ice clouds without precipitation below and at very high altitudes. And if you look at the shortwave fluxes, black line is almost systematically above the red circle. That means we systematically underestimated the simulated fluxes. So for this study, we performed more than 735 HN orbits to check the radiative assessment algorithm. The difference between 3D and 1D fluxes shows that there will be a large negative bias for cloudier or more convective conditions due to the photon entrapment effect. And then there will be a positive bias for low cloud fraction or clear sky condition due to the leakage of radiative fluxes. And then for long wave, the bias or room in square meter error are relatively small. I haven't shown it in presentation, however. When comparing with the series observation, we have small negative bias for clear sky, which need further investigations, and then negative bias for overcast ice clouds, and then also very large but positive bias for overcast mid-level liquid or mixed phase clouds. So these information will be very useful for continued improvement of our satellite processors during the commissioning phase, and also will provide guidance for the planning of calibration validation activities during the commissioning phase. And yes, since the level 2 algorithm development project called Cardinal, so here is a Cardinal birds. And thank you very much for your attention, and let me know if you have any questions.
Thanks very much, Zhipeng. That's really exciting to hear the success of EarthCARE launch and that the deployment for the antenna. It's something we've been waiting so long for. This is really exciting.
Yes. Yeah.
So do we have any questions, Alec?
Yes, we have one question. Could you explain the negative long wave bias of 7.5 watts per square meter when comparing the 3D simulations with series shown in the table on slide 5?
Yeah, I mean, remember, there's long wave negative bias. So one of the possibility of this, because when we look at this long wave, they really depends on the surface temperature, for example. And then we also previously found that, currently in this simulation, the surface temperature we use is from ECMWF's reanalysis, era 5. And for some specific conditions, we find the temperature seems lower than what, if we compare the ECMW reanalysis and then the MODIS retrieval for clear sky. And then we will systematically see the differences of temperature between these two products. So we replace for this results, we replace part of it, but yeah, I mean the surface temperature is very sensitive to those results, and then also the sea surface temperature could also have impact on it. So there are a lot of uncertainties how accurate the surface property could be. So I guess that could be one of the source of the bias. But we still need to look at more cases to understand the contribution of different sources. I hope I clarified this question.
That's great, thanks. Any other questions people have for Zhipeng?
That's it at the moment online.
Okay, I'm going to take the chair's prerogative, but I am going to ask that if Jean-Pierre, if you happen to be in Event Mobi, can you switch over to Zoom so that we can have you give your presentation? So Zhipeng, what's the most exciting part for having the real EarthCARE data, not your simulations? Like what's the part you're really looking forward to?
Yeah, because there's so many uncertainties. All the algorithms developed until now are kind of a virtual, all based on either simulations or other satellite missions. Probably the most direct impact will be, oh, we finally have real data, and then we will check how well or how bad our algorithm is working currently. And at least that will help give us a kind of concrete sense of what's going on. And then based on that, we can continue to improve our algorithm.
Okay. Is there one thing that when you started working on EarthCARE that you weren't expecting? Like just because sometimes we think we're going in one direction and it's like, oh, that's really interesting. Do you see something that's going to come up because you now have the data?
Yeah, for now, probably not. Because what I know is to have those level 2 data, we have to, publicly, we have to wait at least 8 months. But for carve-out purpose, we might have earlier, but these are not matured products. So yeah, and still now we are still probably for the next few months we're still looking at those Atron data to before we get the real data. Yeah, to be patient.
Okay, I'm not seeing Jean-Pierre. Are you, Alec?
Not at the moment, no.
Okay. So we've got a few minutes. So if there are questions that people have for either Kyle or for Zhipeng, I encourage you to put them in the Q&A. I'd like to throw a question at the two of you because we heard very much from Kyle about using operational missions, and Zhipeng's talking about one of our more advanced, science-based missions, because EarthCARE is an Earth Explorer. So each of them is going to have a large, or each of you deal with large data sets. Can you talk about how you see this may change in the future? Are you going to be, as Kyle said, data is getting heavier, so it's difficult to download. Like, what do we see as the way we're going to interact with data? Are we going to move to a point where we no longer bring the data to us, we have to go do our processing somewhere else? Or there's some, what's your feeling on that? And I'll start with Kyle and then I'll throw it to Zhipeng.
Yeah, that's a good question. That's one I would have to leave to other experts on the computational side. But I know, like, from a NOAA standpoint, they want to move everything into the cloud, right? And kind of access data that way or do processing there and then move it. But it really it's an interesting question because, like, with just GOES and ABI, just the amount of data is just incredible. And we're seeing that, and there's the other end of the spectrum where it's like I said with WMS, like static imagery, for example, is really good at looking for loops, but when you're like trying to do that in WMS, it can be jittery, and it really depends on your bandwidth. If you're a user in a low bandwidth situation, that's not going to work. So you got to think about all those other things. And I don't know, like, what the best route forward is. I'd like to see, computation, like obviously, computers would have to, come forward with processing, I think would be number one. Maybe compression algorithms need to change. But I'm not an expert on that side, and it's just questions I really I'm trying to grapple with a little bit. It's just how do you, it kind of worries me in the future. Like even if you had like, let's say like the question that came to me with a hyperspectral imager, like that is just even more data now, but it's useful data. Like it's things we can use in both science and in an operational setting. It's very important.
Yeah, yeah, I think this is one that, as you said, we're going to be grappling with, particularly for NOAA's thinking about it, NASA's thinking about it. I don't know whether Jean-Pierre or Landon will talk a bit about what the plans are on the AOS side, but really, again, it's going into the cloud, having open source, not just data, but open source science, where people can come to the system and do their calculations or utilize code that exists, modify it. And that's going to be a really interesting place to be working. And so it's interesting to hear that it's not just on the science side, but it's crossing into operations as well.
Yeah, absolutely.
Zhipeng.
Yeah. I'm pretty much agree with Kyle's what he's talk about. But in addition to this, I also want to mention this data processing, which is become very heavy too, especially when we try to do the 3D radiative transfer calculation, which is too heavy compared to the 1D. So currently we are kind of investigating if there are any other infrastructure could help for this. For example, using GPU to accelerate the speed of calculation. And then further, I'm not sure, but maybe AI can help, at least to have a model which can imitate very, very well what is standard scientific code is. So that will probably reduce a lot of the calculation load. Yeah.
Yeah, and I just want to expand on that point about the GPU side of things, like the dense optical flow wins that I showed. Those calculations and the software that I have is all done on the GPU. And it brings up an interesting question because like our internal infrastructure, as far as to my knowledge is, there's no particularly for this dense optical flow stuff, it needs an NVIDIA video card because it uses the CUDA package underneath. So that's proprietary, stuff. And so does our computing network internally in the government, are we able to do something like that? Or is it just like, those are things you have to think about. And I think that is always something that management and people externally need to always keep in mind as well, is how we can do this stuff on the GPU way faster, as you mentioned, but other infrastructure has to catch up to that as well.
Yeah, and you're quite tied to that particular platform, which from a government procurement standpoint, I can imagine can add to the challenge and the maintenance and trying to get the best value for money for that.
Yeah, from other projects, certainly from a life cycle maintenance perspective, especially with physical infrastructure that starts breaking down, that can be a real challenge when you have a vendor lock type situation. I'll plug quickly. I see on Thursday, on the final day of the plenary talk, is actually by NVIDIA about AI and machine learning and how that can help with tackling climate change. So I think a lot of people here could have an interest in listening to that talk, given Zhipeng's comments. But yeah, definitely, we're seeing huge growth in the number of satellites, explosion, the amount of data each satellite's providing. Every sensors we're doubling resolution, we're doubling the number of bands we're observing. So this is certainly an issue for us to tackle long term. And definitely discussions well underway in the government and looking towards having some kind of cloud computing infrastructure in the future. So that's work I'm not involved in, talk for another day. But certainly it is being discussed significantly in the government and trying to understand better how we move forward to supporting cloud environments and avoiding vendor lock, et cetera. So thanks for all the insights, everyone. See, we have one
last question for Zhipeng. If you can keep it short, what's the advantage of EarthCARE versus A-Train? If you can do that.
Yeah, for EarthCARE, probably most immediate is all the instruments are on the same platform, and then so we have exact co-located observations comparing to A-Train. Another advantage is the instrument sensitivity is higher, and then also the radar that onboard EarthCARE have Doppler capacity.
Okay. So we're going to stick to the schedule because that's what we've been told by the organizers. So Jean-Pierre, we're going to move your talk to the end after Emily's. Hopefully this will not cause too many problems for Landon, and I hope everyone can stay for the entire thing. So with no further ado, I'm going to pass over to Landon Rieger to tell us about the Ali instrument.
And just really quickly, sorry, Kaley and Landon, for Advanced Systems, our host, if you haven't already granted Jean-Pierre panelist status, please do. Jean-Pierre, there will be a pop-up on your end if you can hear us to accept panelist status. You will need to do that before you can share your screen. Thanks.
So take it away, Landon.
Great, thanks, Kaley and Alec. So yeah, I'll talk a little bit about the HAWC mission, I guess, and then some of the recent campaign work we've been doing from the NASA ER2 airplane. So I'll go just briefly over kind of HAWC here. Anything JP didn't cover, I'll try to get to now, and then I'll talk about the ER2 campaign, some of the flights we've done, and the early results. So HAWC is the high altitude aerosol water and cloud mission. And the goal here is to retrieve co-located information about aerosol extinction, aerosol particle size, cloud top height, water vapor from the ALI and SHOW instruments. And then that's these two instruments, ALI and SHOW, will fly on HawkSat here. And then they're going to be imaging the limb. And then in addition, there will be the TICFire instrument, which is an nadir-looking kind of far infrared imager with 8 bands between 4 and 73 microns. And so this will provide additional information on cloud optical depth, as well as long wave upwelling radiation. And so this provides a really nice closure and link between aerosol clouds and water vapor and their interactions and then their feedbacks on the climate. So that's kind of the 30-second overview of the HAWC mission here. The ER2 campaign that we did was really focused on the two limb scanning or the limb imaging instruments, the aerosol limb imager and the spatial heterodyne observations of water. And so both of these two instruments have the same limb geometry. And so it's convenient to put them both on the same aircraft. And then for the satellite mission, they'll be flown a few minutes ahead of TICFire, and that way they can image the same volume of air simultaneously. But for the aircraft campaign, we're just looking at ALI and SHOW for now. So I'll give you a brief overview of the two instruments that we're flying here. So we have the aerosol limb imager, and this is, it'll take 2-dimensional images of the limb. So flying in the orbit here, it'll look in the image in the orbit plane, looking at the kind of the horizon there, viewing the limb, and it'll take images of about 200 kilometers across track and 45 kilometers vertically. So we get a good image from ground up through the stratosphere. And as it's orbiting, it will take images between 610 and 1560 nanometers, cycling along these wavelengths, as well as swapping between polarizations. And so having both this spectral and polarimetric information provides really nice information on aerosol size, as well as it helps give us some phase information so we can distinguish between aerosols and clouds, which is really important for these UTLS observations. So from these measurements, we hope to have 3 main products. We have the aerosol extinction in this visible and near infrared range from about 8 to 35 kilometers with quite high vertical resolution, about 500 meters. We also hope to get the aerosol effective radius, so a measure of particle size, and then the cloud top altitude down to about 250 meter precision. And then the panels on the right here just show an example of the data we expect from the satellite instrument. So this is a full kind of end-to-end simulation of just one aerosol profile retrieval. where that we have the true state in red, and then the solid blue is the retrieved values. An extinction in the left, and then particle size on the right. The second instrument we're looking at is the spatial heterodyne observations of water. So this is SHOW, and it uses the spatial heterodyne spectrographic technique. And so this also takes images of the limb, but rather than getting horizontal information, the horizontal information is smoothed together and averaged. And so then an interferogram of that is taken, and so you get, on the detector, you'll have vertical information on one dimension, and then you'll have the interferogram in the other, but then that's inverted to obtain the spectral kind of radiance here. And that's what's shown on the inset, will be the kind of the level 1B product from SHOW, which is the spectral radiance. And then this information is used to retrieve water vapor profiles. And the panel on the left here just kind of shows an example of what a curtain of aerosol water vapor might look like from the satellite, where you get really nice high resolution, both vertically and horizontally. It's much higher than anything currently in orbit. So the main product here is water vapor, targeting in the UTLS and stratospheric regions, so about 8 to 30 kilometers, depending on the latitude and how much water vapor there is. Really, the target here is from about 0.1 ppm to 100 ppm region. So kind of in that region that's really sensitive to, or where the radiative forcing is really sensitive to changes in water vapor. And the resolutions are pretty comparable to LE, with about 500 meter vertical resolution and 50 to 200 a long track resolution, same as LE. So onto the campaign work we've been doing here. So the ER2 is a really high altitude aircraft. It has a ceiling up around 20 kilometers. So this provides a really nice test bed for the HAWC limb instruments, especially. SHOW needs to be above the hydropause to really get good information. So the ER2 is well situated for that. And we flew 2 instruments on here, LE, as I mentioned, and this was the first flight for the new elegant breadboard model of LE. So it's a new test of that. And then SHOW instrument was flown previously in 2017. So this is the second flight on the ER2 for SHOW. And then this is kind of how they're mounted on the aircraft in the bottom right panel here. So there's a wing pod, and then SHOW looked out the front of the wing pod to image the limb. And then LE, there's only kind of one forward port. So LE has a periscope that extends through one of the nadir ports, and then the periscope makes it look forward. So they're both imaging the same air mass for good coincident measurements. And so we did 3 flights based at NASA's Armstrong base in Southern California. So those 3 flights are shown on the right here. And the blue one was just a shorter engineering flight that lasted a couple hours. We did a little rosette pattern to look at different scattering angles, but really it was just to test the placement of the instruments in the aircraft and make sure everything was functioning properly. And then we had 2 longer science flights shown in orange and green here, kind of in the following days and week. And the reason kind of we've chosen these particular flight paths is due to really nice satellite overpasses for coincident comparisons and validation. So on the orange one here, we went a little bit further off the coast, and this had a really nice MLS overpass. And then the green one had a really nice OMS overpass for aerosol validation. And additionally, we kind of came back. There's the Table Mountain site pretty close to the Armstrong Air Force Base. And there was also an EPCAPE campaign going on around Loyola. So these provided nice ground-based measurements, as well as balloon soundings that we use for validation. So those are kind of the flight paths, what we were targeting from them. Onto some of the preliminary data here. This is a kind of a panel of one cycle of the LE images. So we go from about 800 nanometers in this version of LE out to 1450. And as you cycle through, you can see kind of the slightly changing patterns in the cloud and how brightly you see the aerosol above it. This is kind of the really nice clear cloud features you're picking up, kind of indicating just the nice spatially resolved data that you get from LE in this panel. And so we have many tens of thousands of images from this campaign, and so they've all been calibrated to level 1 data at the moment. And we've just kind of started to look at the level 2 data. So this is a bit of that. On the right here, I've shown kind of the difference between two polarization states on the LE data. So we've got, basically this is a measure of the cloud detection we're going to use. And we can see up above the clouds, things are pretty flat. And then as soon as you hit the cloud top, you get this kind of sharp transition due to the depolarization of the ice scattering particles. And so this is just kind of a nice indication that everything's working as we expect. And this depolarization measure shows up the clouds really nicely. One difficulty we hit during the campaign was that lining up these images from this kind of slightly jittery aircraft can be tricky. And when you're trying to do the difference between images, you have to do a really good job of lining them up with some post-processing. So the image on the left here is just an example of how we've done some of the altitude calibration from the data. So the left panel is an image from LE. The center panel is something we've simulated of what the ground should look like using kind of a high resolution topographic map. And then on the right is an overlay of those two where we've tried to line them up based on the aircraft pitch and kind of adjusting that slightly. So that's kind of how we're doing the alignment for LE right now. There's still some uncertainty due to refraction and some of the aircraft timing, but generally it works pretty good. And we've done it for a handful of cases that we've used as a test bed. And then if you go to the aerosol retrieval side of things, this is what the extinction profile looks like. So I mentioned that we have some satellite overpasses. So this dashed line here is the retrieval from the coincident satellite measurement. And then the solid line is what we've retrieved from LE. Thank you. And you can see that generally it lines up really nicely. We see the cloud top here. But we also get these kind of like little bumps and squiggles that we actually think are really consistent with the level 1 data, and they seem to be very real. It's just the fact that we're retrieving at a much higher resolution than OMS, so we can pick up these smaller layered features. And it's a pretty similar story for show. So this is just an image of the level 1 B data that's been calibrated, and you can see all of the water vapor absorption lines. As you go to lower altitudes, you can see the spectral, the pressure broadening in the spectrum from that. So the data is looking nice from a level 1B perspective. If we look at the coincident measurements, they also line up really nicely. So this is show in red here, and then a couple of the ground-based balloon sondes that were sent. And the coincident isn't perfect, and the water vapor and the UTLS there can be pretty variable. So you don't expect them to be perfect agreement, but generally things I think are looking really promising from that aspect as well. And then lastly, for the data validation, this is a comparison between the show data on the top, the coincident MLS satellite overpass in the center panel, and then the mirror reanalysis on the bottom. And again, you can see the show picks up the hydropause really cleanly, and it agrees really well with the MLS and mirror water vapor profiles. But you can also see the big difference in resolution you can get in terms of the vertical and horizontal resolution between show and MLS. So it's kind of a nice showcase of that higher resolution data, I think, as well. So with that, I'll just kind of wrap it up. HAWC's a fully funded mission and planned to launch in 2031. So we're kind of ramping up some validation and ground campaigns on that. And this was one of the first one we did fall of last year. And we begin to look at the data analysis. Things look really good, but we just kind of scratched the surface on the science and the analysis we can do from that. So lots of coming work in the current year for that. So thank you.
Great. Thanks very much, Landon. Do we have any questions, Alec?
Don't see any new questions online yet, but I did have one question for you, Landon. I thought it was really interesting seeing the mapping kind of the Ali airborne images to the topography that you were showing, having done similar stuff from nadir looking instruments, trying to get things to align between different data sets before. I had a question on this for you. The field maps that you showed, there's some flight legs over the ocean. So in those cases, I'm assuming you can't really use that same method because you just have a horizon line. At least that could help you a little bit vertically, but is there a bigger challenge trying to do that over the ocean?
Yeah, so the ocean would be nice. Actually, like the horizon is really what we care about. So the in theory, the ocean provides a really nice clean case for that. The problem is that on this particular leg, it was basically cloudy the whole time. So we could almost never see the horizon on the ocean leg. So yeah, we couldn't use that to get the altitude to get the cloud top.
Thanks. Let me just check the Q&A again in the chat. I had one other question, not being a limb sounding person, being still relatively new to atmospheric remote sensing. For the show plots that you had on at the shortest and longest wavelengths, it looks like it's quite a bit noisier. Is that just a change in signal to noise ratio for the different wave numbers? Is that can you explain why we see kind of cleaner looking in the middle versus the edges?
Kind of the noisier parts over here. Yeah, I think this is just a signal to noise thing. Really, we're targeting these kind of central bands. So it's kind of the target and what things have been tuned for, I think. I'm also not a show expert, so somebody might correct me.
Yeah, I'm guessing it might have to do with one of the filters as well, right?
Yeah, there's a kind of a narrowband filter on the front, I guess, that tries to clip out some of this. I'm not sure exactly where the edges of that filter are designed to be.
Thanks very much, Landon. We're going to switch over to now having Emily talk about her work looking at comparisons between the MPLCAN ground-based LiDAR measurements and some simulations from Ali. So please take it away, Emily.
So can you see my screen here?
Yep, and we can hear you well. Thank you.
Okay, perfect. So thank you. So my name is Emily. I am in the first year of my master's at Western University. And today I'm going to talk to you about some comparisons I've made between some LiDAR measurements and measurements from Ali, which Landon was just speaking about. So my goal is to explore whether the Canadian Micropulse LiDAR network, which is called MPLCAN, has the potential to validate Ali measurements and possibly also extend their vertical coverage. So to do this, I'm comparing simulations of LiDAR measurements from MPLCAN with simulations of measurements from Ali, because of course it's not actually up yet. So the challenge with this is that MPL and Ali don't measure exactly the same thing. So the first thing I have to do is develop a method to convert between the two measurements, and then I'm able to run coincident measurements with the two simulators. So in this presentation, I'm going to start by giving a brief introduction to MPL and Ali, and then I'll explain what they measure and then give some preliminary results that I have from comparing them. So the Ali instrument, Landon already gave a pretty good introduction, so I don't have to go into it too much, but just to reiterate, its purpose is to characterize aerosols in the upper troposphere and stratosphere. And we want to do this because currently there's a pretty large uncertainty in how aerosols and clouds interact and how this affects climate forcing. And if you don't know what an aerosol is, it's a particle or droplet suspended in the air. And so the instrument itself is going to be limb viewing, as you can see in the picture on the bottom left. So it's going to be viewing or detecting radiance from the sun that has been reflected off of the Earth or scattered throughout the atmosphere. And it's going to measure the visible and near infrared spectral region, and it also has the capability of separating the light into horizontal and vertically polarized states. So the MPLs, on the other hand, they're not measuring radiance from the sun. They're going to be sending out their own light with a 532 nanometer laser, and then they have a telescope which detects light at the same wavelength, so it's elastic scattering. And you can see it gives us a signal similar to what you see on the right, where if there's an aerosol or a cloud layer, this is going to give us a really big signal because there's going to be lots of scattering. It's also a dual polarized LiDAR, which allows us to measure total volume depolarization, and this is really important to distinguish between aerosols and clouds, because if we're looking just at backscatter, they can look pretty similar, but they have a very different signature for polarization. And this is what our MPLs look like. So we have mini MPLs, and so they're pretty small. They're only about 50 centimeters tall. They also run completely automated all the time. All we have to do is calibrate it, of course, once a month. And so MPLCAN is currently a network of 5 micropulse LiDARs across Canada. We have one in London, Toronto, Sherbrooke, Sandy Cove, Nova Scotia, and then one up in Eureka. And then this summer, we're hoping to get 3 new nodes coming online. So we're going to get one in Alberta and then 2 more in Nunavut. And all of this, there's also lots of MPLs. These are part of MPLNet, which is also all throughout the United States. And I think there's some all over the world, and all this data is open access. So now, before I describe what exactly MPL and ALI measure, I'm just going to give a quick background in radiative transfer just to make sure that everyone's on the same page. So the 2 really important things to understand are extinction and backscatter. Extinction is the amount of light lost when light is transmitted through a medium due to both scattering and absorption. And it's quantified by the extinction coefficient, which is the number density of particles times its cross-section. And this is the summation of scattering from molecules, scattering from aerosols, and then an absorption term. Whereas backscatter, on the other hand, is the amount of light scattered specifically back to the LiDAR receiver. And it's quantified by the number density times the differential scattering cross-section. And it's also the summation of scattering from molecules and scattering from aerosols. So what MPL is able to measure is called attenuated backscatter, and that's given by this equation here. And you can see that that is a function of both backscatter and extinction. And since ours is an elastic LiDAR, we cannot separate backscatter and extinction without assuming something called the LiDAR ratio. And that's simply just the ratio of extinction to backscatter. And this is something that has been measured in literature for different types of particles, but it typically has a pretty large uncertainty associated with it. ALI, on the other hand, what it actually measures is radiance from the sun, but from that we can retrieve more useful quantities like extinction and particle size. So now what I'm looking to do is convert the ALI retrievals of extinction and a particle size distribution into an MPL measurement. So there's 2 different ways that I've done this. The first way is I can just assume a LiDAR ratio and then use this very simple equation to get backscatter. So the problem with this, though, like I mentioned, is that the LiDAR ratio has a pretty big uncertainty associated with it, and it also assumes that we know what type of particles we're looking at to even be able to choose the correct LiDAR ratio. So a second method that we can use is we can use the particle size distribution. So this is something we don't typically, this is information we don't usually have, but it's something new that ALI will provide. So this allows us to calculate the differential scattering cross-section, and I can do this by integrating over the backscattering efficiency times the size distribution times pi r squared. So now to test this methods, I'm using an MPL simulator that I developed, and then an ALI simulator that Landon and researchers at the University of Saskatchewan developed. And what I inputted into these simulations is, just for my first test, I'm just using a simple atmosphere with just background aerosols from the GLOSSAC database. So this is in the presence of no major wildfires or volcanic eruptions. And you can see on the top is what I get when I input this into my MPL simulator. So I get attenuated backscatter, and on the bottom is the extinction and radius that I get from ALI. And these 2 are at different resolutions. So I co-added the MPL data to be at a worse resolution, which is more similar to what we'll see with ALI, because MPL's typical resolution is only like 30 meters. And I also averaged it in time because the MPL data can tend to be pretty noisy. So I averaged it over 2 hours. So then I can convert my ALI measurements into backscatter. And those are the results that I'm showing here. So you can see that with both methods, with the LiDAR ratio and the particle size, that I get pretty similar answers. And the uncertainty that I've plotted here, which are the dotted lines, just comes from the uncertainty in literature on the LiDAR ratio, as well as from assuming that extinction and particle size are retrieved to an accuracy of 10% and 20% respectively. So then from this, now I can compare the LE to the MPL results, and that's what you see here. So what I'm actually plotting is scattering ratio, which just isolates just the aerosol signal, because that's what we really care about. So a scattering ratio of 1 would be entirely molecular. And we can see here that the ALI results in green and the MPL results in blue match pretty well, up to about 15 kilometers. And this is where the MPL's signal to noise drops off significantly. So for such low aerosol loadings that I used in this model, MPL can't really detect things at that high of an altitude. So you can see that the uncertainty increases dramatically and that we don't really have any confidence in these measurements. We can also compare method 1 versus method 2 and see that they both agree equally with the MPL measurements, again, up until about 15 kilometers. So this just shows that clearly I need to input more aerosols into my models for MPL to be able to detect it, to have a more realistic comparison. So that brings me to my future work, which will of course be to run coincident measurements with different atmospheric models, including higher aerosol loadings. That will be more useful for MPL to measure. And ideally in the future, I'd like to simulate the satellite passing over an MPL during a wildfire smoke event. So for this work, I'd like to thank my supervisor, Dr. Bob Sika, as well as my colleagues, Victoria and Basura. And I'd like to thank Landon for showing me how to use the ALI simulator. And of course, I'd like to thank all the sponsors of this project that are funding things like the MPLs and the satellite, as well as my project. And thank you all for listening. I can answer any questions if anyone has any.
Thanks very much, Emily. That was great to hear about how things are starting to fit together as we're building up all the things that we need for HAWC and for AOS. Do we have any questions in the chat?
Nothing in the chat at the moment.
Okay. So while we have, oh, go ahead,
I think
Alec.
there is a slight delay in the event Mobi feed, so I realize we're probably asking this 30 seconds before, we're asking that before the talk ends, so we'll give it a minute to see if anything pops up, but go ahead, Kaley.
I was going to ask Emily for some of the things you wanted to do in future, like the wildfire smoke. What do you think are going to be the biggest complexities to trying to model? Is it going to be sort of stepwise building up the complexity of that model, or do you have all the inputs you need?
Yeah, currently I don't have the input, so that's going to be the challenge, is being able to to input into the simulator. I need to have characterize what the optical properties of smoke are. So we need to input particle size and number density and things like that, which I haven't really done a thorough literature review of that yet, but that will be the biggest challenge for sure.
Sounds like you might, because smoke can be so interesting, it may need to sort of figure out how you want to span the space or look at different aspects, maybe. I don't know. It's going to be cool to see it, though. I look forward to seeing it.
I'm excited.
Okay. I think we have anything yet. Anything from any of the presenters?
No new questions online yet. We've got 2 more minutes and then move on to our last talk.
Well, while we're awaiting the last couple of questions, Jean-Pierre, can you try doing your screen sharing? Just so that, because we didn't get a chance to try that out. So Emily, have you had a chance to visit any of the MPLs yet?
There's one on the roof at Western, so I've been to that one. I've done the calibrations there, but I haven't seen any of the other ones yet. So
yeah. Okay. Yes. Which one's on your wish list, though?
I don't know. It would be cool to go to none of it.
How many MPLs are there?
Currently, there's 5 in Canada, but there's many more across the world. I don't know a number, but by the end of the summer, we should have 8 total because we're getting 3 more.
Yeah, it's really going to be really exciting to see how everything fits together, particularly ones on the coast, as well as the ones in the north.
Yeah.
Okay. In the interest of time, I'm going to thank Emily very much. And can we do a sound check, please, Jean-Pierre?
Yes, indeed. Sorry about the confusion and presentation mode.
Okay.
for
Well,
this
I'm glad
project.
we found you. We have your presentation. So I'm going to suggest that we get started, and I'm going to apologize to people. I am fading very quickly with my jet lag, so if I disappear in the middle of Jean-Pierre's talk, it's not because it wasn't interesting, and I'm sorry to the carbon cycle people, I'm just not going to make it. So I wish you the rest of the session to be good. And Jean-Pierre, take it away. Please tell us
Thank you,
about.
Kaley. Kaley is the lead into the campaign for validation for this mission, and I'm the PI of TICFire, and Adam and Doug are PI for the Alien show, and Jan, Landon, and Jeff, of course, are the strong worker into the deep science there. Thank Emily and Landon for bringing some science. What I want to do is talk on the progress toward the Canadian HAWC mission. So I will skip some of the things that were already said. I'd like to report on the objective of the mission and the status, some key feature of instrument and synergies. You've seen already some of them. Highlight of the campaign, mission, and resource for this project for everyone. So mission objective. A year ago, we had a mission that was, well, the polar orbiter here, and there is the inclined orbit called Storm and Sky, and this is the being changed recently due to constraint into budget at NASA. And instead of the backscattered LiDAR, we have Caligula, which is a Raman data LiDAR, and we have a radar that will be a competed mission coming up. But all the passive instruments have been linked together. The fortunate thing for us is nothing has changed. We're still part of the mission, and the same configuration for us. The interaction with other will be different, of course. So this is the second, this is the HAWC partner for the consortium. And we had the second workshop in November last year. And there's 14 universities, and everybody's welcome to join the group. This is very open science work. And I certainly hope that this will stimulate the research into using space for climate and weather. So I think you've already seen that the Sky mission has the TICFire on board, and then around there is a limb-looking LiDAR, and the important point of that is the synergy between the three instruments, the three Canadian instruments, Alien show-looking limb and TICFire-looking Nadir, and that is an overlap region where all the instrument sees the same thing. And that allows to do a cross-calibration and synergy and extend it outside the scope of each instrument individually. So it's there is 8 objectives to NASA's mission, and I colored here the contribution of our instruments to each of them. So you can see there's low cloud, high cloud, feedback, convective storm, cold cloud and precipitation, and then aerosol, the different aspect and the indirect effect of aerosols. So in one way or another, our instrument will be able to contribute to this, especially focusing on the upper troposphere, lower stratosphere, where NASA is not particularly looking in details. So we really have our own niche. It's a budget of 1.6 billion US that is been capped, but the inflation has caught up on us, and we have to descope some of the aspect, but keep the science as much as possible. Canada has invested over 200 million for our instruments, and CFI has provided us 17 million plus the provincial government another 11 million for the consortium. So this is a really good point to start with. I will skip that, or maybe mention what's specific to our instruments. TICFire has 8 bands, low noise, high radiometric precision, about 2%, spatial resolution better than 2 kilometers. Ali is very sensitive in looking at aerosol, as you've seen before, and it has polarization, which is great for cloud as well. and show as very much sensitive to water vapor. So we're in a position now to look at the interaction between aerosol, cloud, and precipitation and water vapor change in the environment. This dehydration greenhouse feedback that we had postulated way back in the 90s and observed with cloud satellite. So now we can measure it. Our objective is really to look at the nucleation of ice depending on aerosol. So this is very much a problem in model. So some key features, perhaps to emphasize how we interact. The 8 bands of TIC-FIRE allows profiling. You see the 8 bands in transmittance, and where the gradient of transmittance changes, these are Jacobian. This is where the information is coming from, and this is also where the atmosphere cools. And you can see those wave function here. So the long wave, the far infrared, really peak into the upper troposphere, lower stratosphere, upper troposphere. And you can see that show as a very dense limb-looking functions that give very detailed profile. TIC-FIRE give less resolution in the vertical because it's looking at nadir, but it overlaps in the upper troposphere with show. And that is for clear sky, at least, this is a way for us to extend the water vapor. If we look at the other instruments, Ali is looking at aerosol, but also ice cloud. And this is the optical depth compared to CloudSat Calypso when we do the comparison with the simulator end-to-end. And at the other end of the spectrum size, it's the microwave radiometer that takes over. So we really have a good swap of data. Same with the crystal size. We're good in the low end, but the microwave picks up there. It's interesting to see, this is for the first time we have these 5 radiometer covering basically the whole spectrum from solar to the microwave on the same platform. And this is unique at kilometer scale, at very fine scale for some of them. Radiometers looking at 60 angles at sub-kilometer resolution. TIC-FIRE is looking in the thermal and far infrared, looking at cloud and microphysics and radiation. And microwave look deep into the cloud. So we have really a unique set that is never been done before. So the end-to-end simulator is starting with atmospheric scene and doing radiative transfer and doing the instrument simulator at the engineering level with optics, sensors, and electronic, getting the level 1 data and calibrating the data and then comparing with the input. So we have a closure and we can verify. This serves a lot for us to guide the industry into doing some compromise in the technical side and also to develop algorithm and to study the synergy between the instrument. This is really a power, and it's going to be available to other users to work with us. An example of the requirement this year has been spent into the engineering aspect because we are going from phase 0 to phase A. And we have to provide to the industry all the specification that will ensure that we have the quality that we need. And this one example is for the instrument radiometric resolution for TIC-FIRE, but it's for all the instruments. We had to do similar exercise to find the goals, the threshold, and look at the limitation and the implication for different conditions. So this is a big exercise. Another aspect that I'd like to point out today is the notion of fingerprint. EarthCARE is looking at the full IR. TIC-FIRE is looking at the 8 bands. So it's really there's a unique one-to-one correspondence between the set of measurement by filter and the physics and the radiation and the cause of the cloud formation. So you can see here a number of points taken from Eureka from the ground, and it changed from time to time very much so. And that fingerprint is unique to the physics that has led to these clouds. And we want to invert that to find the crystal size, the microphysics, and the properties that leads to that. In some way, if the model are able to reproduce the fingerprint for the same type of cloud, it would be a very strong constraint for improving the physics. In clear sky, you can see that it's very flat. So the precision into we have to add all the kind of source of errors like the winds and the jiggering of the satellite and the optics and some other, and this gives us about 2% precision. And you can see the amplitude is about 40 watt per square meter. So 2%, the width of this line is about the precision of the measurements, combining all the errors. So this for different cloud. And on the right-hand side, you see the different bands. And the spectral signature will be how does the music will play on different frequencies, if I can say so. So this will be a very stringent data set for model improvement. Just to put it in figure, we know that clouds are depending on many processes, and it is selective. Each bits of the cloud depend on some distribution of processes, and the formation of cloud is very much a threshold effect, 1-0 kind of things. So vapor to droplet, condensation, freezing, precipitation, they're all step kind of function. This means that it's very sensitive to any change in the physics. So that makes it very constraining. If we go at kilometer scale and we sample the signature, the fingerprint of these, we will demand the model to have the same kind of signature and the same kind of clouds. So this will be a very, very strong, much stronger constraint than EarthCARE. So this is saying the same thing, just to illustrate this point. So I'd like to highlight some campaign and mission and resource to finish. Landon has talked a lot about the campaign with the ER2. We didn't have the TICFire on board, but we have the simulator to compare with measurement to the ground, calibrate, and bring virtually the EarthCARE, the TICFire on board, either from space or from the aircraft, to see what kind of synergy we can have with the other instruments. Now, there is another campaign in preparation in 2020 January. It will be the first time that we go into the Arctic during winter time. That's Zhipeng and Zen Mariani and Alec Kovalev that work on it at CCC. So we will have a campaign for the first time to test ALI and TICFire on real atmosphere. Now, science and application timeline, there's a budget, that's a very substantial budget that is distributed mostly for science grant. It's going to be for the next 12, 15 years. There's a grant of different kinds. There is a suborbital study. There is an application to models. There is flight and campaign. So this is really for the community, the Canadian community, to work on this project, to get the best of the science that we can make out of our instruments. So just to finish, the 2007, we had the first generation with CloudSat Calypso. Tremendous success there. That was the starting point. That's at the time where I thought about TICFire. So the 2024, we have now EarthCARE and PreFire. That is the second generation. And the third generation will be the EOS HAWC that has some advanced technology that will look differently at the same kind of problems. It's a very important problem. So I'll finish with this. Thank you.
Great. Thanks very much, Jean-Pierre. Looks like Kaley has had to drop off. So we thank her for co-chairing up to this point. I'll just take a quick look, see if there's anything in the chat or in the Q&A to this point. I don't see any new questions yet, but again, there's a bit of delay for the stream to the public, so we'll wait a moment to see if any questions come in. But thanks for the excellent talk, Jean-Pierre, and to all the other presenters. While we take a moment to see if any questions come in, I'll remind everyone that we have part 3 of the Satellite Earth Observation section coming up in the next session, starting at 3:55, so in about 20 minutes from now. So for any of the panelists, any of the presenters in that next session, Ray, Paul, or Jean-Philippe, please make sure you join the Zoom. If you don't have the Zoom link yet, please, well, I think some of you have my email, or ping me through the EventMobi app, and we'll join during the break. And I don't see anything on the chat yet. So we'll wait another minute to see if any questions come in. And feel free to add questions for any of the panelists, any of the presenters, not just for Jean-Pierre. And we've got a couple minutes before the break. Kyle, go ahead.
Yeah, that was an interesting talk, Jean-Pierre. I mean, a lot of it's over my head, but that last mission you were talking about, the polar night mission, is kind of an interesting one. Like, forgive my ignorance, but like, would these instruments be able to sample near the surface? Because I'm interested in, from like a blowing snow perspective, like to see like water vapor or something like that close to the surface, because that's really important for blizzard generation, and it's a lot of questions that we have in the Arctic.
That's a good question. I don't know the exact answer. The aircraft is not meant to fly very low. We did NetCare before, which had the advantage of being able, with John Abbott, being able to fly slower and lower. In this case, we would be flying above stations at time, like Eureka, for instance. So if there is a ground measurement at the same time, that would be interesting to compare the two data sets. But I'm not aware. Would be a question to ask for Alex or Zen, for instance. Maybe it's a special request. So, yes.
All right, I don't see any more questions on Event Mobi, so I think with that, I'll say thanks again to all the presenters for the wonderful session. I encourage everyone to come back for part 3 after the break and part 4 tomorrow, and enjoy the rest of the week online for CMOS, and hope everyone, if you're presenting later in the week, make sure you find your Zoom links. And thanks everyone for joining the first 2 of these sessions, and we'll see some of you back for session 3 after the break.